Welcome back to the Ephemeris Podcast. Hopefully, you all are doing all right as you're listening to the podcast. I'm obviously your host, Aphelion. If you're new to the show, then that is new information to you. This is the 10th episode of the podcast, and it's a good feeling to be about 3 months into this thing and still going strong because I was like, I don't want to crunch out too many episodes very quick, and so I decided, okay, let's do every Sunday. Sunday's a nice day to kind of have some of the podcast episodes go out and give myself a week to kind of be able to plan for it in case I wasn't able to do it in 1 day or 2 days. And yeah, we're 10 episodes in, which means we're 10 weeks in, which means we are 3 months of the year into this podcast. And I'm pretty proud of myself for being in this position because a lot of the other content creation stuff that I've done in the past has ultimately died before it even had a chance to, hit the ground. So, anyways, that was a bit of a tangent. Considering or reflecting on last episode, there's just a couple things I picked up. Essentially, I think when I was explaining the whole star pulsating thing, it would have perhaps been a little bit helpful to kind of talk about oscillation and just really the basic physical concept of oscillation, because that's what you want to imagine when you're thinking about a star pulsating. It's kind of an oscillation on the astronomical scale. But other than that, just getting rid of the verbal static, which I just did. I'm still working on that. I noticed it quite a few times, but it's getting better. It's getting better because I'm avoiding from just constantly giving out this sound to keep my voice flowing throughout the whole episode. I'm taking gaps, taking breathers. It's all right. I don't have to, run through a bunch of verbal static just to keep the episode going. It's unnecessary and it just kind of ruins my speech. So I'm still working on that. And let's actually talk about today's episode. Jeez, I'm rambling a little bit. So today's episode is a mini deviation for the last few episodes, and in retrospect we've been heavily focused on variable stars, and I promise to get into that in maybe the next one or two episodes, continuing that train and talking about luminous blue variables, because I mentioned that, but it's another important piece to variable stars as a whole. But that's not this episode for mainly one reason. It's that I kind of need a break, more of a breather of an episode, because my life's getting kind of busy right now. Science Olympiad, regionals, competitive stuff is happening, and I have to keep up with that. And also, a couple classes are picking up the pace because, we have testing that we have to get prepared for. So, yeah, my life is getting a little busy, so I'm taking a little bit of a breather for this episode just to make sure that I can accommodate for other things in my life. And I hope that I won't have to do too many of these episodes, but there's a chance that I will, especially getting into the end of the calendar year, 2023. I might struggle with putting out thorough 20-minute episodes every single week because of the things I have to do other than the podcast. So anyways, this is one of the few quote-unquote breather episodes that we're going to call it, just because I've just been using the word. So today's focus is on the Fulton Gap, and me coming up with this idea for the episode was essentially me looking through astronomy terms, but I don't quite want to describe Fulton Gap as just a simple astronomical term, because there's more to that, and there's a reason why I picked it for this episode. It's because it's more than a term. So there are heavier implications with the discovery of the Fulton Gap that I want to talk about today. So that's what we're going to do. Let's dive right into it. To understand the Fulton Gap, we have to graze over planets and exoplanets because they're going to be mentioned throughout this whole episode. Now, everybody and their mothers knows about the 8 planets in our solar system, and some of the focus of NASA and all of these big space organizations is looking at maybe other planetary systems that are like our solar system, and looking at planets that revolve around stars that are around us in the Milky Way galaxy, right? So everybody and their mothers is familiar with these ideas if you have, paid attention to any space science. There are gaseous and terrestrial planets that can exist in a planetary system. That's pretty obvious because whenever we're talking about our solar system, we say, hey, there are gaseous planets and there are Earth-like planets, right? So those are the 2 types of planets that we're very familiar with, on top of the fact that we're very familiar with planetary systems. But there are 2 more types that I do want to mention that might come up later in the episode. It's that there are Neptunian planets, which are similar to Neptune and Uranus, kind of in that ice giant category, and they're hydrogen and helium heavy planets with rock cores. So a little bit of solid in the middle and some gaseous atmosphere. And then there's the super Earth, which is heavier than Earth but lighter than ice giants. So it's kind of in the middle of looking at terrestrial planets, and looking at Neptunian kind of planets. So what's significant about all these types of planets that we know about is that where you can get planets like Earth, which are mostly rock, some atmosphere, but not significant to the degree of some of the other atmospheres we see. There are planets that are made mostly of gas on the other side of the spectrum. And then there are in-between planets, but these ones tend to be more massive than the Earth at all cost, right? So then that begs the question, what about Earth-like planets in the middle, right? Why doesn't that come up in terms of the types of planets that we look at? Well, this is a dilemma that rose from the findings of the Kepler mission, essentially. Right, so Kepler mission launched in 2009, sought to understand planetary systems and the habitability of planets around certain stars, and kind of it looked to determine all shapes and sizes of planetary systems. And this one is kind of the predecessor of TESS, which we'll talk about in a moment. But as a whole, Kepler and TESS, both missions, they have confirmed 5.7 thousand exoplanets. They have found almost 10,000 candidates, and they found almost 4,000 planetary systems, right? But the most important conclusion that Kepler data yielded is that planets 1.5 to 2 times the radius of Earth are very rare. And this discovery did come in a single research paper that was published by Benjamin J. Fulton, and hence the name, the Fulton Gap. Right, so in this research paper, Fulton used California Kepler survey data and demonstrated this phenomena using it. And let's kind of break down what exactly happened in this research paper that led to this whole thing. So Fulton and all other authors involved, they started with the full survey data of the California Kepler survey, and they narrowed it down. And the exclusions from the data were, and I don't think it's limited to this list, false positives of exoplanets, planet-to-star radius uncertainties, and basically what that means is the most common method of getting exoplanet data is to analyze it as it passes in front of the star. And so doing that will yield a planet-to-star radius, which is helpful, but if it is extremely uncertain for this research paper, presumably, it's difficult to create accurate results. So maybe a little reasoning behind why they included planet-to-star radius uncertainties as an exclusion. The next exclusion was low transit probability star, and from what I grasped, I understood it as them saying if the planet was very unlikely to have been in transit when we were looking at it, then kind of unnecessary for our data, right? And then the last exclusion from the data was imprecise stellar parameters due to temperature. And that's basically how I'm going to leave that one. That one has, if you want to get into the specifics, it's like they were looking at planets in a specific Kelvin range, and it was a bit of a long explanation. So I'm just going to leave that one at that. So after the exclusions, when a histogram sort of graph was plotted, and this is based on my visual observations of the research paper, right? So the histogram had the number of exoplanets on the vertical axis and the Earth radii on the horizontal the Earth radii on the horizontal axis. Right, so when they made this histogram sort of graph, they noticed that there was a significant dip in the number of exoplanets between 1.5 and 2 Earth radii. And it was described in the paper as essentially a gap in the quote-unquote bimodal distribution of small-sized planets. So in this case, we're considering Earth-like planets to be very small, and everything above that Fulton Gap to be closer to Neptune, but still small. So what's the hot theory behind why this happens then? Well, the theory is that this gap is caused by the unwillingness of planets to have a balance of solid and gas at this particular size range. So what that means is essentially either planets are too small to hold on to their huge atmospheres, or stars become too massive because they hold on to their atmospheres. So either the atmosphere is a significant factor in the size of the planet, or it's not because the planet kind of can't hold on to it. Now, in terms of the future of elaborating on this Fulton Gap, because it's literally just a single research paper, right? There's not yet enough data collected by TESS, which is the successor of Kepler. But there isn't enough, data from that, and astronomers still suspect to see this gap with the new data. However, that's kind of the end of the story for the information that we do have on the Fulton Gap, because again, the research that's gone into this is a single paper, and the rest is pretty much up to speculation. But I do want to point out one last thing that I think might have a loose connection, may not be relevant, but still I kind of see it as there being a loose connection here. The article mentions that the Fulton Gap, by the paper's definition of super-Earths and sub-Neptune planets, is right in between the two, right, without the numbers. And if you look at Neptunian planets, they tend to follow a path around what's called the hot Neptune desert. And what the hot Neptune desert is, it's this lack of hot ice giant-like planets that keep their solar radius as they get warmer. So let me elaborate on that, and kind of the process of hot Neptunes and why it's not possible for them to keep their solar radius. So as Neptunian planets, they reach a temperature of 900 degrees Celsius, or if you just add 273 to that, that gets to about 1200 Kelvin. It is theorized that Neptunian planets lose their atmosphere because the star heats it up so much that the atmosphere escapes the gravity of the planet. However, there are a couple of planets that break the cycle, but again, for most part, right? They don't break the cycle, and they just tend to lose their atmosphere, right? So there might be a chance that many Neptunes, which is a subtype of Neptunian planets that are smaller than Neptune but bigger than Earth, there's a chance that these things either break the barriers of the Fulton Gap or help explain it. And that might sound kind of out of whack. So let me kind of visualize this for you. Let's imagine we have a Neptunian planet. It's like a couple Earth radii, right? And it's getting warmer, and we put its path on a plot, a rectangle plot, right? So as this Neptunian planet that's about, like, let's just call it like 5 Earth radii, as it's traveling from the right side of the plot, which is pretty cool for some of the Neptunian planets, and it's traveling left, getting hotter and hotter, right? It approaches the area of the plotted graph that's the hot Neptune desert. And if it kind of falls in line with the rest of the Neptunian planets that we know, it's either going to go more towards the top of the plot, which is like hot and big in terms of Earth size, or it's going to follow this path downward into an area that's like about 1 to 2 Earth radii in terms of size, and it'll get really, really hot. So if we imagine the process and how it travels across this plot, we can imagine that the Fulton Gap would happen because as these Neptunian planets get hotter and hotter, their solar radii decreases, and they're not able to reach this point between 1.5 and 2 solar radii where they're able to keep their atmosphere. They just have to go lower on that plotted graph. And so that's one thing. But if we look at the Neptunian planets that have broken this cycle, we might be able to say, well, hey, there are these anomalies. They get larger and larger, but they keep their atmospheres. Can we find more of these things that are kind of in the lower half of that Neptunian desert, parabola shape in this plotted graph that's towards the left of the plot, right? So that's kind of what I mean by there is a chance that this process of Neptunian planets losing their atmosphere might explain why there's this divide. However, there is a slight issue with this kind of theorization and visualization of what might be possible with the Fulton Gap by using Neptunian planets and how they act when they get hotter. It's that the hot Neptunes don't actually reach a temperature that is satisfactory for us to be able to analyze them when we look at the Fulton Gap, because in the research paper that did find it, they kind of looked at planets that were in about the 4,000 to 6,000 Kelvin range, and the hot Neptunes that we're talking about here, when they get to the hot Neptune desert, only reach about 1,200 Kelvin. So if we think about that, that makes kind of this whole theorization and visualization a little bit useless. But I think it's kind of cool if there's a chance that we expand our parameters to be able to look at more planets and we get down to that 1,200 Kelvin range. There's a chance that Neptunes kind of come into the mix here, and how the hot Neptune desert works and all of that jazz. But that is all I have for today's episode. Hopefully you guys have enjoyed listening. It's a bit of a tangent from the variables again, and the intention was a little bit more to, make a light episode, but I still think it was a pretty interesting topic to go over, because there are these little, nice bits and pieces to astronomy terminology that we can really learn from. So if you guys enjoyed listening to the podcast episode, make sure to follow me on Spotify if you're listening on Spotify, and if you're listening on YouTube, I would really, really appreciate a subscribe. If you're coming from the shorts, thank you very much for viewing. I know that short form content tends to be a thing where it's like people really, really enjoy that and don't want to have to come to the long form content and listen to the whole shebang. But if you guys are here watching the full episodes, I really, really appreciate it. And until next time, peace.